Would black holes be the key to a quantum theory of gravity, a deeper theory of how reality, of how space and time works? Well, I think so. It's interesting. These objects, which have been known, I would say, for 40 or 50 years, but theoretically for the best part of a century, have always been fascinating. They're odd things. The simplest way to describe a black hole would be a region of space from which even light can't escape.
Black holes are some of the most puzzling objects in the universe. They are surrounded by what's known as the event horizon, a region where their gravity is so strong that even light cannot break free.
Black holes are interesting because we have a place called the event horizon, where we think that we have full control of the physics. We understand what's happening, but there is a fundamental clash between our two basic theories of nature, both quantum theory and general relativity together. And the quest to unify those two great pillars of 20th and 21st century physics into what's often referred to as a quantum theory of gravity is in some sense a holy grail for theoretical physicists. So black holes are forcing us into a deeper understanding of what space and time are. And in that sense, I think it is fair to say that black holes are the keys to understanding the universe.
Matter that falls near this point is gone for good. These objects have such intense gravitational pull that they can bend light itself, trapping it completely. They exist throughout the galaxy, scattered across space, with a massive black hole sitting at the center of the Milky Way. This one is about 4 million times more massive than our Sun. To spot a black hole, scientists look for very fast-moving objects around an invisible center. They assume that's where the black hole must be.
The old picture of black holes, and Stephen Hawking believed this for a long time, had a bet about it actually, is that they seem like they destroy information. You can just kind of see it goes to the end of time, right? It's gone. And then they evaporate away, and it seemed that there was no way, even if you gathered all the Hawking radiation that had come off for trillions of years, there's no way you could reconstruct what went in. So therefore, if you jumped into a black hole, you'd be erased from the universe. But that breaks pretty much every law of physics, right? Things don't erase information. They scramble it up, make it difficult to read, but they don't destroy it.
The exact origin of black holes and how they connect to the broader universe is still unclear. But recent discoveries by scientists have opened a new chapter. They've managed to look into the heart of a black hole for the first time. What did they find? Is it as terrifying as we've imagined? Let's dive into the details of how scientists were finally able to see what's inside a black hole and what happens if you were to fall inside a black hole. Famous physicist Brian Cox has shared an interesting perspective.
Well, there's an event horizon surrounding the black hole. In some sense, it defines the boundary between the external universe and the interior of the black hole. And if you go across the boundary into the interior of this sphere, then even if you can travel as fast as the speed of light, you can't escape the gravitational pull of a black hole. But another description of the event horizon, which confused people all the way through the history of black hole research actually, was the idea that the event horizon, when viewed from the outside, is a place in space where time stops. Now that's a direct prediction of Einstein's theory of relativity from the external perspective. There is a central problem though, which is still not solved, which is what lies at the center of a black hole.
Black holes have captured the attention of researchers and everyday people alike for generations. According to Einstein's theory of relativity, time is the fourth dimension, tightly linked to space. In this view, gravity isn't a force like we normally think of it. Instead, It's the result of mass curving the fabric of space and time. You can picture this like placing a heavy bowling ball on a trampoline. The weight of the ball stretches the fabric, creating a dip that nearby objects roll toward. In a similar way, black holes, known for their enormous density, create deep curves in space-time that nothing can escape from. Scientists are still working to understand exactly where matter ends up once it crosses into a black hole. But overall, the trampoline comparison helps us grasp the idea. All matter nearby gets pulled into a dark, deep pit that nothing comes out of.
Described by Einstein's theory of general relativity, they are distortions. In Einstein's theory, they're distortions in space-time. And their distortions are so extreme that there's a region from which light can't escape in this space-time. So the classic example is the collapse of a massive star, which essentially the history is that in 1916, so only just a few months after Einstein published his theory of general relativity, Karl Schwarzschild showed how space and time are distorted outside a perfectly spherical, non-spinning ball of matter. So it's a solution of Einstein's equations. So it tells you the distortion of space-time outside a star, a simple model of a star. Now, it turns out that in those equations, if you just keep the distortion but remove the star, but leave the mathematics there, then you have the description of a black hole. So it's in there. And actually, interestingly, if you allow this solution to go infinitely far into the past, and so you just have this, you kind of continue it into the past, you get a description that's not only a black hole, it's a wormhole with a black hole and two universes and a white hole and one bit. So it's all there in the mathematics from 1916. So they're very natural in that sense. The question becomes, as we said earlier, does nature create such things, given that it can exist? Can nature do it? And that was the debate, actually, into the 1930s.
The term black hole was first introduced in 1967, though the concept dates back much earlier. In 1783, John Michell suggested that invisible but powerful objects might exist and could be detected if they orbited close to stars. Building on Michell's early ideas, researchers in the 1930s applied Einstein's theory to explore how stars might collapse under their own weight, forming black holes. Michell's theory was proven in the 1970s when astronomers Paul Murden, Louise Webster, and Thomas Bolton observed a massive, unseen object orbiting a blue star about 6,000 light-years away. This object was named Cygnus X1, the first confirmed black hole. This discovery confirmed that even though black holes are invisible, their presence can still be detected. Today, scientists estimate there could be up to 400 million black holes in our galaxy alone. And across the observable universe, around 2 trillion galaxies are believed to each contain a supermassive black hole at their center. That means clusters of galaxies could hold hundreds or even thousands of these enormous black holes. Thinking about the size and number of black holes makes you wonder how many other cosmic secrets are still out there. Their incredible power raises more questions about what else might be hidden in the universe. Black holes are extremely dense objects with powerful gravity due to their massive size. This gravity is so intense that not even light can escape it. It's now widely accepted that both spiral and elliptical galaxies contain black holes in their cores. There are 3 main types of black holes. First, there are stellar mass black holes. These are the smallest, typically ranging from 1 to 100 times the mass of the Sun. They usually form when a large star's core collapses after a supernova explosion. Then, there are supermassive black holes, which are millions or even billions of times heavier than the Sun. These huge objects are thought to grow by merging with other black holes and absorbing nearby stars. In between these two extremes are intermediate mass black holes. Only a few of these have been found so far, and they have masses between 100 and 100,000 times that of the Sun. They're considered the building blocks that may eventually merge into supermassive black holes. Studying black holes helps us understand strange star movements and gives new insights into our galaxy. According to general relativity, massive objects like black holes warp space and time, which is what creates gravity. Because of how densely packed their matter is, black holes have some of the strongest gravitational forces we know of. But things become even more confusing when we look at the center of a black hole, known as the singularity. In this region, gravity becomes so intense that scientists can't fully agree on what's happening there.
Actually, it's not right to talk about the centre of a black hole, really. So what are we picturing? It's this thing called the singularity. You might think of it as an infinitely dense point to which this massive star collapses. It's kind of the natural way to think of it. But actually, just even in pure general relativity, when you look at a nice map of a black hole, the so-called Penrose diagram named after Roger Penrose, what you see is that the singularity is not really a place in space at all. It's a moment in time. And actually, it's the end of time.
Einstein's theory suggests that when something falls into a black hole, its information disappears forever. But quantum physics disagrees, claiming that such loss of information shouldn't be possible. This conflict has turned black holes into a testing ground for some of the most advanced theories in science. Because of this, black holes have become valuable tools for studying the fundamental laws that govern the universe. They offer a place to test theories from general relativity and quantum mechanics, and even ideas from string theory. Many people wrongly assume that black holes are just empty holes in space. In reality, they're more like incredibly powerful magnets. But instead of pulling metals, they use gravity to pull in matter of all kinds. Gravity is what keeps us anchored to the ground when we jump. Earth's gravity constantly pulls everything toward its center, but that pull ends once we reach the ground. A black hole is completely different. It has no surface to stop you, and its gravitational pull is far stronger than Earth's. That overwhelming pull into what feels like an endless fall is how black holes got their name. It's widely known that black holes form when massive stars collapse under their own gravity. This collapse forces all the star's mass into an extremely small space. The more mass something has, the stronger its gravitational pull. That's why gravity isn't just the Earth pulling on you. You're also pulling back on the Earth, although your pull is much weaker. Since Earth is massive compared to a human body, its gravity dominates. That also explains why astronauts feel lighter on the Moon, because the Moon has less mass and therefore weaker gravity. So if black holes aren't actual holes, what are they? Technically, a black hole exists in three-dimensional space and is shaped like a sphere. It has two main parts, the singularity at its core and the event horizon, which is an invisible boundary around it. The singularity is found right in the center. It's a point where density becomes nearly infinite, and it has no physical volume. Despite being infinitely small, it holds all the mass of the black hole, and its gravity pulls everything nearby toward it. This tiny but incredibly dense point is what gives a black hole its power. Think of it like this. If you're standing at the North Pole, the northern hemisphere pulls on you more than the southern one does, simply because it's closer. That shows how gravity works stronger the nearer you are. Now imagine compressing all that mass into a much smaller volume. That concentrated mass would increase gravity dramatically. This extreme density is what separates a regular star from a black hole. A black hole's mass is packed so tightly that its gravity becomes nearly unstoppable. The event horizon is the outer boundary of a black hole, the point where nothing, not even light, can escape once it crosses over. This is the part you often see in visuals as a black circle in space. While it might seem like a physical edge, it isn't made of any substance. It's more like a border in space beyond which everything is pulled inward at incredible speed. It's important to understand that black holes are not solid objects. They are mostly regions of space with almost nothing in them. The only matter is at the core, within the singularity. Everything outside of that is just space where light and matter can no longer escape after crossing the event horizon. The gravitational pull of a black hole is so strong that even light cannot get out. Because of this, black holes cannot be seen directly. Instead, scientists study them using giant radio telescopes and by detecting gravitational waves. Back in 1915, Albert Einstein suggested that objects moving through space cause ripples in the fabric of space-time. He explained that space and time are connected and can be bent or stretched by gravity, similar to ripples on a pond's surface. Jump to the year 2015, and scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, made a major discovery. For the first time, they detected actual gravitational waves. These waves were created by two black holes crashing into each other about 1.3 billion years ago. Today, black holes can be found by looking at how they affect nearby matter. They pull in gas, dust, and even stars, heating them up and causing them to release high levels of radiation that can be measured as heat or X-rays. Then, in April 2019, another big milestone was reached. Using a network of 8 radio telescopes known as the Event Horizon Telescope, scientists captured the first ever image of a black hole and its surrounding shadow. This black hole is in a galaxy called Messier 87, which belongs to the Virgo galaxy cluster. It's about 55 million light-years away from us and has a mass 6.5 billion times greater than that of our Sun. The image showed a glowing ring of light around the black hole, which is caused by superheated gas spinning near the event horizon as it falls inward. Whenever black holes come up in conversation, people often wonder what lies inside them. But falling into a black hole isn't something anyone would want to experience. The outcome depends on the type of black hole, but neither is pleasant. If you fell into a stellar mass black hole, for example, you'd go through a process called spaghettification. It sounds silly, but it's terrifying. The gravity would pull harder on your feet than your head, stretching your body into a long, thin strand, like spaghetti. Now, if you're the kind of person who'd rather explore for science than fall into a black hole by accident, you might look toward a supermassive black hole like Sagittarius A. This one is found at the center of our Milky Way galaxy. It stretches around 44 million kilometers across and holds the mass of 4.31 million suns. Although it was discovered in 1974 by astronomers Bruce Ballack and Robert L. Brown, it wasn't officially named Sagittarius A until 1982. The moment you pass the event horizon of Sagittarius A, your one-way trip begins. From the inside, you'd be able to look outward, but no light from you could reach the outside. Interestingly, although the gravitational pull of a supermassive black hole is stronger, the tidal forces, the ones that stretch you, are actually weaker, so you might avoid getting spaghettified right away. But escape still isn't possible, unless one day we find that white holes, which are purely theoretical at this point, offer a way out. To put it simply, if black holes pull matter in, white holes might do the opposite, push it out somewhere else. These two concepts, while different, are connected through something called a wormhole, which acts like a tunnel between them. The theory suggests that after billions of years, a black hole could turn into a white hole. But that's still a long shot. Inside a black hole, time moves so quickly for you that the transformation would feel almost instant. This is all still in the realm of theory, and scientists are constantly refining these ideas. But just for a moment, imagine entering a black hole to run experiments that could expand human understanding. There's a possibility that matter inside doesn't get crushed into an infinitely small point. Instead, it may be compressed into the smallest possible structure that still occupies space. This idea is called a Planck star. It comes from a theoretical framework known as loop quantum gravity. Loop quantum gravity is a speculative attempt to create a quantum-based version of gravity. It breaks space and time into extremely small pieces. These pieces are so tiny that our normal movements still seem smooth. This idea of a grainy universe does two things. First, it supports the goals of quantum mechanics by giving gravity a quantum explanation. Second, it helps avoid the problem of singularities inside black holes. As a star collapses and its gravity increases, space-time's discrete nature keeps it from compressing past the Planck length, which is about 1.68 times 10 to the negative 35th meters. Everything falling into the black hole gets squeezed into an incredibly tiny, but not zero-sized, ball. Since the compression can't continue forever, the material eventually pushes back outward. Saying it expands might be a gentler way of putting it than explodes. This means black holes might not last forever. However, from our point of view, due to time dilation near a black hole, this process would take billions or even trillions of years to complete. Another idea that tries to remove the singularity without relying on quantum gravity is the gravastar. The name may sound like something made up on the spot, but astronomy sometimes adopts quirky labels. The key difference between a black hole and a gravastar lies in what's inside. While black holes are thought to contain a singularity, gravastars are filled with dark energy. Dark energy is a real and mysterious force that exists everywhere in the universe. It's believed to be driving the expansion of the cosmos. This isn't science fiction, it's a genuine part of our universe. When matter falls onto a gravastar, it doesn't pass through the surface. The thick concentration of dark energy at its core stops anything from crossing the event horizon. In appearance and behavior, gravastars can seem almost identical to black holes. It's important to understand that the event horizon of a black hole marks a critical boundary. Once anything crosses it, not even light can escape. But recent data collected through gravitational wave detectors like LIGO and Virgo, especially during black hole collisions, has raised new doubts about the gravastar theory. If gravastars were colliding instead of black holes, the wave patterns would look different. So far, what we're seeing doesn't support the gravastar idea very well. Planck stars and gravastars aren't the only theories out there. There's also a more traditional view of black hole singularities that tries to better match what we actually observe. The concept of an infinitely small, dense point comes from our understanding of simple, non-rotating black holes. But those types are rare and not all that interesting. In reality, black holes usually spin, and that changes things. When a black hole spins, its singularity doesn't stay as a point. It stretches into a ring. According to Einstein's general relativity, if you somehow cross through that ring, you might find yourself passing through a wormhole and coming out through a white hole in another region of the universe. But rotating black holes have problems of their own. Their insides are highly unstable because of the rapid spin of that ring-shaped singularity. This spin creates strong centrifugal forces, which act like anti-gravity in relativity. They push things outward rather than pulling them in. This dynamic forms something called an inner horizon inside the black hole. At this point, outside radiation gets sucked in by gravity, but near the singularity, that same radiation is pushed away by the anti-gravity forces. The inner horizon is a critical transition zone. If you ever reached it, you'd be hit by radiation, carrying what feels like the entire history of the universe, all within a split second. That's how much energy you'd face. This adds another layer of complexity to our understanding, especially since many of the black holes we observe are spinning. It might mean that our current equations don't fully explain what's going on inside. Fortunately, a breakthrough in physics, gravitational waves, has opened up a new way to study black holes. Thanks to this, researchers now have a tool to understand what happens during some of the most extreme events in space: black hole collisions. Back in 2015, scientists made a major discovery. They detected gravitational waves for the very first time. This was done using enormous and precise instruments designed to pick up tiny ripples in space-time caused by black holes crashing into each other. These collisions send out waves that travel across the universe. Since then, this method has helped scientists identify nearly 100 black hole mergers through the signals they leave behind. To make sense of it, scientists often compare it to shaking a box and listening to the sound it makes to figure out what's inside. In this case, the shaking is the collision, and the sound is the gravitational waves. These signals are now being used to improve the models that describe cosmic events. The goal is to better understand what's happening inside black holes and see how well Einstein's theory holds up under extreme conditions. Earlier models focused only on linear interactions. These worked for a while, but they couldn't explain every detail. Now, newer research involving nonlinear interactions is showing better results, improving accuracy by up to 10%. This could also help us detect even more black hole collisions in the future, helping us prepare for the next phase of gravitational wave research. This advancement could lead to deeper insights about how gravity works and what really happens in the far reaches of the universe. LIGO, the main observatory for detecting gravitational waves, has been offline since 2020 due to the pandemic. But newer systems are being built and are expected to start running soon. These will allow for even clearer observations of black holes and what they're doing. Now let's discuss what Brian Cox says about going inside a black hole. He describes the center of a black hole, the singularity, as literally the end of time. Once you cross the event horizon, all possible paths forward in time lead directly to that singularity. There are no detours, only that point lies ahead. A Reddit discussion quoting Cox clarifies, "When one falls into the black hole and hits the singularity at the center, Brian Cox states that you have hit the end of time. Hitting the center becomes a fixed point in your future at the end of time. So, from your own perspective, you're marching inevitably toward the singularity and there's no return." Cox says you would see the outside universe speeding up. You'd witness its future unfold quickly, but only for a limited moment, until you hit the singularity. Again, from that same Reddit thread, the universe would appear to speed up, but you'll still only get to see a finite portion of the remaining lifespan of the universe before you reach the singularity. Even though you're being pulled apart, stretching feet first and squashing from the sides, Cox points out the detail depends on rotation and tidal forces. Your body would twist, stretch, maybe even form internal waves before it's torn apart. So thanks for watching this video. If you enjoyed watching it, give it a thumbs up and subscribe to our channel for more content.